Good afternoon, welcome back. Just was discussing with the excellent staff here that today would be the 30th lecture. We have about 10 to 12 lectures more to go. So we're getting to the end. Just a quick recap of what we did last time. Last time I started the new topic of LDPC codes, and the discussion was part motivation and part explaining terminology. So I pointed out why it is that this class of codes is known as LDPC codes, which stands for low density parity check codes. And I told you that whereas in a typical matrix the number of ones in the matrix would be of order n squared, in the case of an LDPC code it is typically on the order of n. And a second difference is that LDPC codes are described in terms of their parity check matrix, and while it is customary for the entries in the parity check matrix, the rows to be linearly independent in what we have discussed up to now, when we come to the topic of LDPC codes, it turns out that needs some relaxation. So we will just say that the null space of this matrix defines the code, but we relax the requirement that the rows be linearly independent. Then we introduced a subclass of LDPC codes known as DV-DC regular codes, and here the property of these codes is that from the point of view of a parity check matrix, every row has an equal number of ones, which is equal to DC. Each row stands for a parity check. The columns have a constant number of ones, DV, and these columns of course stand for the variable nodes, stand for the code symbols. And then of course there is if the matrix is of size m by n, there is this simple relationship which you obtain by just counting in two different ways the number of ones in this matrix. And then from that you can actually derive a simple inequality relating to the rate of the code, namely that the rate of the code is greater than or equal to 1 minus dV by dC, and this is called the design rate of the code. LDPC codes are typically visualized and people work with them in a graphical, from a graphical perspective, and what that graphical perspective does is that it puts one node for each code symbol on the left, one node for each parity check on the right, and makes appropriate connections. So for example, in this particular code, the code length is 10, there are 5 parity check symbols, so that the parity check matrix of the code is of size 5 by 10, and then we have a 1, for example you have a 1 in the 8th row and the second column, 8th row and the second column if there is a link connecting these. And so that means that you can visualize all these edges as telling you that, as identifying the code symbols which need to sum to 0 under this parity check represented by A. This graph is bipartite, it is called the Tanner graph. Then I pointed out that decoding of these codes is carried out using a sequence of message passing, and that is very similar to the way in which we pass messages across in the junction tree. And that because under the DV-DC regular condition, the degree of each node is a fixed constant, that gives the decoding complexity, which is typically a function proportional to the number of edges in this graph, is linear in the number of code symbols. Okay. And just to make the connection with what we had discussed earlier, here was a junction tree for a code defined by this parity check matrix, and however you can redraw it in the form of a Tanner graph. This code however is not an example of a DV-DC regular code, and you can actually see that. However, it still does have representation in the form of a Tanner graph. So maybe it is worth just making that a quick note. Note this code is not DV/DC regular. All right. So, that brings us to today's lecture. So, today's lecture, so this will be lecture 30. And I am going to call this very simply LDPC code terminology. Of course, we have already looked at some of the terms that we are going to come up with, but we will continue this because this will allow us to build up a vocabulary which we will need when we discuss the performance and method of operation of these codes. So, a very quick recap. Introduced LDPC codes. We introduced terminology of DV/DC regular codes. We talked about the rate. Then we talked about the tanograph. And of the decoding complexity being linear. All right. So, today we will discuss these codes some more, and so perhaps what I will do is I will begin by drawing a graph, and we will call upon this graph several times over the course of the next 2 or 3 lectures. So, it is going to take me a couple of minutes to set up this graph, and so let me do that first. Okay, so I'm going to give this graph a name and we'll call it the computational tree. And now you might ask, well, what relevance does this have to us? So let me bring back our earlier lecture. And I am going to copy over this particular graph here. Okay, here we go. I am going to remove some of this notation which we do not need at this time. All right. So, we have this Tanner graph, and what I mean by this computational tree, which you see here, what I mean by this here is that I am going to actually unravel this graph by starting from a particular node. So, I might start from a check node, go back to the variable node, see which all nodes it leads to, and so on. So, basically this is redrawing the graph in a different way, okay. But apart from that, nothing has really changed. So, here what it means is that I have a variable node which is connected to these 3 check nodes, and each of these is connected to variable nodes and so on. Now, I have numbered these 1 through 21. So, I want to make it clear that this computational tree does not directly reflect correspond to this particular code. See, this is a code whose block length is 10, but clearly since I have variable nodes going up to 21, this code has block length at least 21 and typically much larger. Okay, so, I do not mean to indicate that this is these two codes are the same, but nevertheless for given any Tanner graph, you can always unravel the graph, so to speak, and draw it in this form. Okay. And now what I am going to do is give you a few definitions involving notions of edge and path and so on, and those have to do with this computational tree. So, for example, I will be talking about the edges that we will be talking about will be directed edges. For example, 17 to I, that is an example of a directed edge, okay, and I to 21 is a second directed edge, and by path we will mean a sequence of directed edges. So, a sequence of directed edges would represent a path. The neighborhood of a node up to a certain depth is basically a collection of edges and nodes that is traversed by paths whose length is at most d. For example, if you are looking at the neighborhood of this node of depth 1, then that would include these 3 nodes and these 3 edges. If you were to go to depth 2 and look at the depth 2 neighborhood of this node, then that would include these 2 edges, these 2 nodes, these 6 nodes and these 6 edges. Okay. So, we will actually make formal definitions of these right now. So, I will call this edges and paths, edges, paths and neighborhoods. So, clearly it is clear what we mean by an edge. So, here if this is a variable node and if this were a check node, let me draw that a little bit more clearly. So, let us say that this is a variable node and let us say that this is a check node, and I am typically going to try to represent check nodes with rectangular boxes and variable nodes with circular. So, if I write V comma C, then this is a directed edge. Okay. On the other hand, if I were to write say C comma V, then that would be a directed edge, but going in the opposite direction. Okay. So, now that you understand what a directed edge is, then a path in the graph, and if you ask the question which graph do you mean, well, it could be the Tanner graph, except that I am thinking of it when it is redrawn as a computational tree, okay. But it really is a reference to the Tanner graph. So, we will just say Tanner graph. A path in the graph is a sequence of directed sequence of directed edges of the form E1, E2, E sub k, such that if EI is equal to UI prime, then EI plus 1 is equal to UI plus 1 prime, and UI prime is equal to UI plus 1. Okay. So, in other words, we are thinking of these two edges as being contiguous and leading from one to the other. So, this is a common vertex or a node. Okay. So, from UI we are going to node UI plus 1, which is the same as this node, and then we are going to go to this node. So, this is what we mean by a path, and we say that the length of the path is, for example, here there are k directed edges. So, we will say that the length of the path is k. So, it is the length of the path is equal to the number of directed edges along the path. Given two nodes in the graph, we will say that the two nodes are at distance d if they are connected by a path of length d, but not by a path of length less than d. Then we define NUD. This means the neighborhood of node U to depth d, which should be taken to mean the induced subgraph consisting of all nodes reached and all edges traversed by paths of length at most d and starting from U. So, let me see if I can illustrate this last definition here. We did that once earlier, let me just repeat. So, if you are talking about the neighborhood of node 18 to depth 1, as I pointed out just a short while ago, that includes all nodes that are reachable by paths of length at most 1. So, that is 1, 2, 3, 4, and all edges traversed along those paths. So, that is 1, 2, 3. So, that means that this collection of these forms the neighborhood of 18, and I think we can actually use a little bit of our technology. Let me see if I can do that to indicate that. So, let us see if we can put that in red. Okay, I am having a slightly harder time trying to color these edges red, but anyway I think you get the idea. So, these 4 nodes are in the neighborhood and also these 2 edges, except that I am having a hard time converting these edges to, maybe I will try the simple way. Let me do this so that I do not leave you confused. Let me draw these. Okay. So, that is now the neighborhood. So, this then is the neighborhood of node 18 to depth 1, all right. All right. Then there is a simple claim at this point. Note that U1 belongs to N U2D if and only if U2 belongs to N1 of D. That is, and that is fairly simple, because what that means, going back to the graph, is that for example, I belongs to the depth 1 neighborhood of 18, and it is clear that the reverse is also true, that 18 belongs to the depth 1 neighborhood of I. Now, in a similar fashion, if E is an edge we see, then the undirected neighborhood of E is NV union NCD. Then the undirected neighborhood to depth D of the directed edge is this, all right. So, again getting back to the graph. So, for example, if you are here and you are asking what is the undirected neighborhood of this to depth 1, that means that it is the one depth neighborhood of this node as well as this node. So, in this particular case it would mean, let us see if I can get the colors right this time, it would mean perhaps no, that is going to be hard. So, I am going to have to do it the hard way. So, that would in this case mean okay. So, this would so then if you are talking about the edge from 18 to C, then the one depth neighborhood of this edge is the union of the one depth neighborhood of this and the one depth neighborhood of this. So, that is why everything that is shown in red is actually included in this. There is also a notion of an undirected neighborhood of the directed neighborhood. So, this will be our last definition with regard to edges. The directed neighborhood to depth D of edge E equals VC denoted by NED is the induced subgraph containing all edges and nodes on paths E1, E2, ED starting from V but with E1 not equal to E. So, just a clarification, earlier we talked about the undirected neighborhood. So, the undirected neighborhood is indicated by an E, except that you do not put the arrow. Okay. Now, most of this will be clear from context, even if it is a little confusing now. And here the only difference is that it is similar to the earlier definition, except that the initial path is disallowed from being the original edge. So, for example, in this graph, if I were to talk about the directed neighborhood of this directed edge, that means that I can start from here and I am allowed to walk along paths of length d, except that I am forbidden from actually starting out on this link. So, that means I can walk, let us say I am interested in going to depth 4, then I can go to depth 4 in any direction except this one. Okay. So, that is what he means by the that is what is meant by the directed neighborhood, and the difference in terms of notation is that we put an arrow on the edge. All right. Here you can actually prove that now there is nothing particularly important about V and C being like this. You could also start with a C and you would have an analogous definition in which you talked about the directed neighborhood to depth d of an edge of type C comma V, and it would be defined in an analogous fashion. Another small note to note here is that here you can prove this yourself. If E belongs to n E prime of d, then it must also be true that E prime belongs to n E of d. So, there is a reciprocal relationship, but at least intuitively it is obvious. It takes just a little bit of work to show it, but we will not get into those details. All right. So, what have we done? Let me just quickly recap. So, it has been a lot of terminology, basically talking about edges, paths and neighborhood. I defined what is meant by a directed edge, and then I talked about a path being a string of such edges, contiguous edges. Then we talked about the length of a path, and we talk about the distance between two nodes in the Tanner graph, and then we talked about what we meant by neighborhood of a graph, and we talked about neighborhood of a node, neighborhood of an edge, the directed neighborhood as well as the undirected neighborhood. As I said, the reason for going into such detail in the terminology is because when we talk about decoding, we will be in need of it. So, next we will talk about channels. So, the two channel models that we have in mind are, first of all, the binary symmetric channel, and we have already seen this before, and you know that the binary symmetric channel looks like this. There are two inputs and two outputs, except that our inputs earlier were 0 and 1. This time, however, our inputs will be x t equal to 1, x t equal to minus 1, and similarly the output you will have 1 and minus 1, and this will represent the output, and the crossover probability will be epsilon. Now, note that this channel you can actually represent in the following way. We could represent y sub t in the form x x sub t into z sub t, where here this z sub t is either plus or minus 1, and the probability of z sub t taking on plus 1 equals the probability of z equals 1 minus epsilon, and from that it is clear that the probability that z t is equal to minus 1 is epsilon. Okay. Now, this terminology is a little different from what we have been used to. Typically, when we encounter the binary symmetric channel, we actually view it as being additive, and we are working in the 0-1 domain. So, in case that puzzles you, what you can actually keep in mind is that this x t can be regarded as minus 1 to the u t, and where it is the u t which is either 0 or 1. Okay. So, this is just a small change in notation for the symbols, but actually it makes things easier. Okay. So, we will view the input and output as plus minus 1 rather than 0 and 1, and the conversion is just via minus 1. So, 1 here really stands for u t equal to 0, and minus 1 corresponds to u t equal to 1. And I have just pointed out that you can represent this channel multiplicatively, that is, you can pretend that the output is obtained by multiplying the input symbol by a particular symbol, which can take on plus minus 1 values with these probabilities. The other channel model we have in mind is the additive white Gaussian noise channel, or more precisely the binary input additive white Gaussian noise channel. Which typically we have been representing it like this. We have an input and we have an output, and let us say that the input x t is again plus minus 1, then the noise that is added to it is distributed, has a Gaussian distribution. So, it is normal with 0 mean and various sigma squared, and then what you have here is y of t. So, y of t is equal to x of t plus n of t. That is the typical representation, and keeping in mind the nature of the Gaussian density function, I can draw the following picture. Okay. So, what I mean to say is that the plus 1 and minus 1 here are your input, and what you are looking at here are the density functions of p of y t of y as y. Now, perhaps I should do the following. Let me okay. So, just to avoid confusion, let me redraw it slightly differently. I am going to draw this with in red. Okay. So, what I mean by this is that if the input is a +1, then y of t has this PDF, and if the input is -1, then it has this particular PDF. Now, here again the interesting thing is that this is the customary representation, but again you can give it a multiplicative representation, because you can write y of t as being x t times z t, where z t is normally distributed with mean 1 and variance sigma squared. Okay. And you assume that x t is z t is independent of x t. Statistically, it is independent of x t. All right. So, why does that make sense? Well, if you just think about it, let us say that x t is 1, then y t is z t. So, it has this density function, because the mean is 1, the variance is sigma squared. Let us say x t is equal to -1, then y t is minus z t, and its density function will look like this. But that is exactly what we had even under the additive representation. So, we will actually switch to this multiplicative representation. Okay. Now, notice one thing, that in this particular case, supposing I asked you to compute P of y t given x t of y given x. Now, that is easy to see that that is precisely P of z t given evaluated at y divided by x, and it is also easy to see that this is also equal to P of y t given x t of minus y minus x. The reason being because this is again of minus y by minus x, which is P z t of y by x. So, okay, now it seems strange to actually do this calculation like this. What you are actually saying is that the probability of the density function at y corresponding to a certain x, if you reverse x, you will have the same density function for negative value of y, and you can see that here. Supposing x is -1, let us say, and you wanted the density function at -half, you would be here, but that is the same as the density function of y equal to +half when x is +1. Okay. If you reverse both quantities, then the value of the density function remains the same. Okay. This is a fact that we will use shortly, and this is known as the channel symmetry condition. All right. And I want to point out that the same channel symmetry condition also holds in the case of the binary symmetric channel. So, let us check that. P of y t given x t of y given x is again P of z t given y by x, okay, which is equal to P of yt given xt of minus y given minus x for exactly the same reasons as before. Okay. So, the comment here is that so this is known as the channel symmetry condition as applied to the binary symmetric channel. Okay, good. Now, what we want to do is introduce some terminology associated with message passing. So, let me label that message passing terminology. So, let us go back to this figure here. So, this is the tanagraph, and as I mentioned some time back, the way we are actually going to decode this code is by actually passing messages back and forth along these edges. So, we will actually start, let us say, from the variable nodes, pass a message along this edge to the check nodes and back and forth. Okay. So, we will be doing this iteratively, and the way the iterations are numbered is that there is an initial or 0th iteration in which messages flow from the variable nodes to the check nodes, and then you start your iteration 1, which is a flow of information from the check nodes to the variable nodes, followed by a flow of information from the variable node to the check node. So, that would be the first iteration, then you would have the second and third and so on. Okay, so, messages are going back and forth, these are the variable nodes, these are the check nodes. Now, initially if you think about it, the variable nodes are the ones that will actually initiate message passing, because they are the only ones who have any information at hand, and the information that they get is actually the information that they get from the channel input. Okay. So, that channel input will then they will use to actually determine or compute the first set of messages that they pass out. Now, all of the messages that are being passed out are real numbers. Okay. So, all of them are actually real numbers or a subset of the real numbers. And now, what we would like to do is we would like to just introduce some notation relating to the alphabet of these messages. So, we will actually draw a graph, a picture as I introduce this terminology. So, here is your variable node, and here is the input from perhaps I should just use a solid line since I am using a different color anyway. So, let me just use a solid line here. This is the input that it receives from the channel. So, we will make a note of that. And then on the other hand, it also receives input from the check nodes. And what it does is that it sends back a message to the parity nodes. So, it's over here, somewhere over here there is a parity node, there is a parity node, and the message that is going back is also going back to a parity node. Okay. Now, all that we want to do is we want to identify the alphabet which is used to pass these messages, or the alphabet corresponding to these messages. So, this alphabet, which is the channel output alphabet, will be called O. Okay. So, the message alphabet will come from O. This message alphabet will come from script M, and so will this. Okay. So, then O is the output alphabet of the channel, and M is the common alphabet employed to pass messages from variable node to check nodes or vice versa. Okay. So, here we will this diagram was, so to speak, centered around a variable node, but you have a similar picture at a check node. So, at a check node we would have, and then you would have your variable nodes, which are communicating with the check node. And here again the messages are from the alphabet M. Okay. So, we will note that both O and M, so maybe I should write it out in words, both O and M are subsets of the set R of all real numbers. And so, basically, just to summarize, since we just have a couple of minutes left, what we did was we continued developing terminology of LDPC codes that will enable us to, it will make it easier for us to discuss the decoding algorithms. So, I introduced the notion of an edge, a path, and of a neighborhood, of the length of a path, and then we talked about channel models. I introduced the binary symmetric channel from a multiplicative through a multiplicative representation, and did the same for the additive white Gaussian noise channel. These are the two principal channel models that we will be looking at. And I introduced the notion of channel symmetry, and then we were just getting into the alphabet that is used to actually pass messages. And so, let me just close by writing down an equation which I will continue to develop in the next lecture. Or maybe this is a good place to stop. We'll introduce the notation next time. Okay. All right. Thank you.